Recently on the Houdini Discord, there was the question of how you would break up this standard mushroom shape that happens in a very symmetric smoke simulation. And someone, I think Varo from Varomix Training, pointed to this video on Vimeo. And in here, some really talented guy going by the name of Benny showed a technique that he came up with to break up the symmetry of the smoke simulation. And what he does, what you can see here, is he scatters points in space depending on the pressure of your simulation and then uses the distance to these points to mask a turbulence field to break up the smoke simulation. And this technique produces really nice results. However, what I want to do here is I would like to build this without having to scatter points into your simulation and instead purely stick to volumes or fields as they're known in simulations. So in Houdini, first thing we want to do is build a basic smoke simulation. Geometry, drop down a sphere, in this case scale it down to 0.3, then drop an ISO offset to quickly convert this into a density volume. Let's set the sampling distance to 100, just highlight this. Okay, that worked. And now drop down a DOP-net and we're going to build the smoke simulation in there. So just a basic smoke simulation consisting of a pyro solver, which goes into the output, and it needs a smoke object, and to create some source for it, a source. In the source volume, we'd like to point the source path to our ISO offset here, and in the sub to DOP bindings, we want to bind density to density, and we also want to bind density to temperature, and we don't want to bind velocity like this. And now if we hit play, we can see something happening. The resolution is very coarse and the bounding volume is too small, so let's fix both. Let's set the division size of the bounding volume to 0.02. So the resolution increases. And also what I want to do several things in the pre-solve step. So I'm going to drop down a merge node, wire this in the pre-solve here. And the thing about DOPS that irritated me when I first started is DOPS is not a data flow graph. So these connections don't necessarily mean that data flows between those nodes. It's an execution graph. So the order of these nodes tells Houdini in which order to execute operations on a given object, in this case on a smoke object. And the order of operations is from left to right and top to bottom. So in a merge, everything I'll wire in here will be executed from left to right. And the first thing I want to execute is a resize. So I want to resize and adjust the size of my bounding volume depending on the size of my simulation using a gas resize fluid dynamics node, which goes in the merge here. And let's increase the padding to say 0.5. So when I hit play now, nothing happens, no resizing, because I did not check or uncheck the clamp to max bounds here. So now my simulation dynamically scales, dynamically resizes, and I can see this mushroom cloud evolving here, this very symmetric mushroom cloud. Zoom out a bit, like this. So what I want to do here is I want to create a volume, or a field as they're called in DOPS, containing a mask for the turbulence. So I need to create an additional field, an additional volume, which I'll use as a mask. I'm going to create that with a scalar field node, and I'll wire this in between the smoke object and the pyro solver here. And let's copy over those settings here by just copying these parameters like division size, and paste them in the scalar field settings as well. So right click, paste relative reference, do the same thing for the size, and let's just check in the gas resize fluid dynamic here. We want to tell Houdini to resize this field here too, so let's just give it a proper name and not just call it scalar field, but turb mask for turbulence mask. So in the gas resize fluid dynamic, we also want to resize that, the turb mask, like this. Let's get up one level and just re-import the data from a simulation here using the DOP.io. And I'm just going to drag in my DOP-net here and select my smoke object as the DOP node. And then as a preset, I'll just choose smoke, which will by default import 4 fields. And in reality, I only need the density now. So let's attach a volume visualize and let's crank up a density scale. Hit play. And I can see my simulation coming in there. Let's copy this DOP.io, and in here I'd like to import my pressure field and attach a volume slice to visualize this. So this is my pressure here, and let's set this to black body and dial the range to something that makes sense, like this, -0.1 to 0.1. Copy this another time, and in here I'd like to import and visualize the field that I created called turb mask. That still is empty because I'm not doing anything to it except from creating it. Let's just, in the volume slice, set the range from 0 to 1. So let's call this vis_turb mask. This is vis_pressure. and this is vis_smoke. And what I want to do is I want to use the values in my pressure field to quote-unquote scatter points in the areas of high pressure. And I want to scatter these points, or to write data on these areas, into my turbulence mask field here. So in the DOP.NET, let's drop down a gas field wrangle. A gas field wrangle is just a volume wrangle for DOPs. Now what I want to do here is, on the one hand, use a noise to kind of scatter areas into my turbulence mask, and on the other hand, drive this noise with my pressure field. So where the pressure is high, the noise will come through. Where the pressure is low, there will be no noise, so the mask will stay black. Let's create a few parameters for that. First, the frequency of the noise, the speed with which the noise undulates, changes, 2 ramps to dial in which parts of the pressure field to mask, and how strongly the contrast in my noise will be, and also a coefficient to cool down that field so that the mask kind of fades away after a while. Let's first create a frequency slider. Then a speed slider. Then a slider for the cooldown coefficient. And 2 ramps to dial in where the noise will appear. And the pressure ramp takes in a parameter which I call P, which we'll have to create first. So let's create another float. And we want to use the values stored in the field in the volume pressure, so that can be just bound with F at pressure. However, I'd like to fit this. If you remember, and let's head up 1 level. If you remember my pressure visualization, you can see the values I dialed here are in the range of -0.1 to 0.1. And in my gas field wrangle here, I want to fit those to be between 0 and 1. So let's use a fit function for that. And let's fit the pressure, which in our case ranges from -0.1 to 0.1. Let's fit it in the range of 0 and 1, like this. Next, let's generate the noise, which we'll use to simulate this scattering effect. And for that, I need a position, and I'm going to use the X noise, that's the simplex noise function for that. And that, as you can see, needs a vector 3 or better a vector 4 to work. We're going to use a vector 4 to drive this, not only using the position in the volume, but also to make this noise undulate a bit with the 4th parameter, which will be the time. So let's create this vector first. Call it noise position. And it should be equal to our current position's X component times the frequency. Let's just copy that here. Paste it 2 more times and change the component to Y and Z respectively. And finally, the 4th component will be our time multiplied by the speed. So we can dial in how fast this will undulate. Let's generate the noise, and we only need a single float value. Let's call this one check. And let's use the noise position to generate that. Also, let's use a ramp to dial this in. Call this noise_ramp, like this. No errors so far. So now what I want to do is I want to check if the value that I just generated of the noise is smaller than the probability value that I generated with ramping the pressure here. So if that is smaller than probability, then I'd like to set my float value for the turbulent mask to 1 in our case. But as we'll see later, I'm going to blur this out, this field, so this value will lose a bit of strength. So I'd rather set it to a higher value, for example, 32. Now the only thing left to do is, for each step, I would like the turbulent mask to fade away a bit. And I'm just going to do that with multiplying the incoming turbulence mask value with our coefficient, just to dampen it, to cool it down, to reduce the value of the turbulence mask in each simulation step. Okay, let's create all those user interfaces here and dial in those values. And I spent quite a lot of time figuring out some sensible values here. So the pressure ramp goes from 0.45 to 0.6. The noise ramp goes from 0 to 0.25. The noise frequency should be set to 6. The speed to 10. And the cooldown coefficient to 0.6. And again, it took me a while of trial and error to come up with those values. But for this simulation, they seem to work. Let's save this, head up one level, reset the simulation, and let's visualize the turbulence mask. And you can see those dots appearing there and then fading away depending on the pressure. Let's stop that and visualize the pressure too. Yes, and you can see that is working. Now what I want to do, those are really harsh and take a while to fade away. So what I like to do is, after I created this turbulence mask, I want to blur it out using a gas blur, which will wire in the merge. The field should be the turb mask. Let's set the radius to 0.15. Go up again, highlight the turbulence mask visualization, and hit play. So now my scattered areas just disappear, fade away, and are blurred nicely. Okay, so we generated this mask. So back into the .NET, put this aside, and what I want to do is add a gas turbulence here. And in the gas turbulence node under control settings, I want to check control field and link up my turb mask. Also in the general turbulence settings, and again, just values I came up by trial and error. So scale, I'll set that to 5, swirl size to 0.3, and the turbulence to 4. Like that. Let's head up, visualize the smoke, and hit play. Let's just check this does not look too right. Let's visualize the turbulence mask. Head back into the .NET. Let's visualize the turbulence here. Oh, one thing I forgot is to set the control influence to 1, so it's only driven by the turbulent mask and not by anything else. Let's reset this, up one level, hit play again. And of course, first check, visualize smoke. Yeah, that is looking better. The smoke only gets affected in the areas with high pressure up here. So that is my take on this brilliant technique to break up the symmetry of a smoke simulation. Again, what we did is, in the .NET, we used a gas field wrangle to read out our pressure field, remap it with a bit of fitting and ramping, and then combine it with the noise we generated to create a mask, which we used to drive the gas turbulence here. And the trickiest thing about this, I find, is realizing how DOPs actually work, the underlying principle. And again, that is just an execution graph. So in this case, this small network here tells Houdini to use this object and execute this thing first, then this. Then we go to this node. We can see there's something attached here, so we go up. Something other is attached here, so we execute this. Back here, back up, then this. So we go back down to the pyro solver, then this node here, and finally the output. And that works a bit differently than SOPs. Once you wrap your head around it, a few things suddenly get easier. However, there are still some quirks around DOPs, so I'm not 100% sure if I really like it, but it's a really versatile system, so it's worth investigating. So that is how you break up a smoke simulation. I hope you had fun. I'm looking forward to seeing your artwork. See you next time, and it's cheers and goodbye.